students built a cosmic radio to search for dark matter. In an impressive demonstration of scientific ingenuity, a team of undergraduate students has designed and operated a compact dark matter detector capable of probing one of the most profound mysteries in modern physics. Using modest resources and institutional support, the students built a simplified experiment to search for axions, hypothetical particles, widely considered leading candidates for dark matter. If you like my videos, subscribe my channel and press the bell icon to turn notifications on, so you keep getting all the major advancements in science and technology. And don't forget to like and share this video with your friends and colleagues. Comments are welcome and open for discussion. Although the experiment did not detect axions directly, it successfully placed new limits on where these particles may still be hiding. The result shows that meaningful contributions to frontier physics are not restricted to billion-dollar facilities or multinational collaborations. Carefully designed small-scale experiments can also generate valuable data. The study was published in Journal of Cosmology and Astroparticle Physics. Why dark matter matters. Astronomical observations indicate that ordinary matter, stars, planets, gas, and dust accounts for only a small fraction of the total matter in the universe. The rest appears to be an invisible substance known as dark matter, detected only through its gravitational influence. Dark matter helps hold galaxies together, shapes large-scale cosmic structure, and influences the evolution of the universe. Yet, its fundamental nature remains unknown. Among the most compelling candidates is the axion, a very light and weakly interacting particle originally proposed to solve a problem in quantum chromodynamics, the theory of the strong nuclear force. If axions exist, they may also form a vast background field permeating our galaxy, meaning Earth is continuously moving through dark matter. A student-built detector, the student researchers from the University of Hamburg constructed what is essentially a simplified cavity haloscope, sometimes described as a kind of cosmic radio. This type of detector works by searching for the tiny conversion of axions into microwave photons when exposed to a strong magnetic field. Under the right conditions, axions passing through the apparatus could generate an extremely faint electromagnetic signal at a frequency related to their mass. To build the instrument, the students assembled resonant metallic cavity precision electronics, measurement instrumentation bilateral supports, and shielding aids access to a strong magnet. The design intentionally focused on the thumb. Essential physics while minimizing cost and complexity. How a cosmic radio works. The detector functions similarly to tuning a radio receiver to a specific station. If dark matter axions have a particular mass, they would convert into photons at a matching frequency. By scanning narrow frequency ranges with a resonant cavity, scientists can search for a tiny excess signal above background noise. Because the possible axion mass range is enormous, no single experiment can scan everything efficiently. Instead, many experiments explore different regions of parameter space. Even a compact detector with limited sensitivity can contribute by eliminating possible masses and coupling strengths. Scientific results without a discovery. The students did not observe a statistically significant signal attributable to axions. In frontier physics, however, a non-detection is often scientifically valuable. Their measurements allowed researchers to exclude certain axion models within the frequency range tested, particularly particles that would interact relatively strongly with photons. This helps narrow the search space and informs future experiments about where not to look. In effect, each exclusion result improves the map of dark matter possibilities. Why this achievement is important. This project demonstrates several important principles in modern science. 1. Frontier physics can be scaled down. Large collaborations remain essential, but smaller experiments can still test meaningful ideas when carefully designed. Education can produce real research. Students were not merely reproducing known laboratory exercises, they were generating publishable scientific constraints on a major unsolved problem. 3. Innovation often comes from simplicity by reducing complex dark matter experiments to their core functional components. The team created a practical pathway for low-cost exploratory research. Connection to larger dark matter programs. The students were supported by researchers connected to Mad Max Collaboration, a major project pursuing axion detection with much larger and more sensitive instrumentation. This relationship highlights how educational and large-scale science efforts can reinforce one another. Major collaborations provide expertise and infrastructure, while smaller projects cultivate talent and novel ideas. Could dark matter detectors become teaching tools? One especially interesting suggestion raised during peer review was that if axions are eventually discovered and their mass becomes known, compact detectors like this could become standard university laboratory instruments. Instead of scanning unknown frequencies, future students might tune directly to a confirmed axion signal and study its properties. That would transform today's frontier experiment into tomorrow's classroom apparatus. The broader message: this study is not only about axions, it is about accessibility in science. It shows that with creativity, mentorship, and focused engineering, even early career researchers can participate in answering cosmic-scale questions. Dark matter remains one of the greatest mysteries in physics, but progress can come from many directions, not only giant observatories, but also determined students building a cosmic radio in a university lab. Conclusion: by constructing a compact axion detector and producing new experimental limits, these students demonstrated that meaningful dark matter research can be achieved on a small scale. While the universe did not reveal its hidden matter this time, the project successfully reduced the space where dark matter may exist. Sometimes, even listening quietly can teach us something profound.